Alright, we're back. Continuing on with some stuff I read in comments and stuff. We're going to go, being I kind of rushed through it a little bit yesterday when I was doing Kirchhoffs Laws on the Wheatstone Bridge. I went ahead and wrote it up bigger because I figured on the paper it would have been a little hard to see, and we're going to kind of go through it and take a little more time. So basically what we got is we have a 13-volt supply, battery supply here, that's hooked to a Wheatstone bridge. This is a Wheatstone bridge. Now these are used in various circuits. Like I said before, a lot of times you'll find a meter right here where this 1 ohm resistor is right here. And it basically, the bridge becomes a balance type circuit. It balances so that the current going one direction and current splitting going the other direction. If these currents are exactly the same, this will read 0. If one's a little greater than the other one, then you're going to get a meter movement, or at least current through here, which if it has a meter, it's going to move. Now generally what you do, if you're hooking this up for a meter, then one of these points, either here or here or here or here, one of these will be where your meter leads are, or where you connect in something that you're measuring. And that's what will end up changing the characteristics of the current going through on each side of this and throw the bridge out of balance. Now, that being said, let's look at the Kirchhoff analysis of it using Kirchhoffs. And primarily all we're using is this loop law more than anything else. We are looking at the current also, and of course that's what we're figuring out. We have established that we'll have 3 different currents because of so many legs that's in this, so many branches. So we have I1 here, I2 here, and then crossing the bridge we have I3. So that's what is known as 3 unknowns. We do not know what these currents are. So in order to work the problem, then we have to have 3 equations. The thing about simultaneous equations, which is what this is, and how you figure out Kirchhoffs laws, is the number of equations are the number of variables or number of knowns. So if you have 2 unknowns, you only need 2 equations. If you have 3, you need 3, 4, 4, and so forth. Since we're going to make these up with the loop law, then we have to establish some loops. Now we can pick, to a certain extent, there's really a few different paths that we can look at. The path that I picked was, the first one is right here. So it goes from the battery through this resistor and then back to the battery. That's it. Just this color. That's it. That's number 1. That's all we're looking at. Number 2 will follow from the battery around this resistor back to the battery. And that's it. And then number 3 picked up here, so it's just these 3 resistors in this little loop right here, and that's all we're looking at there. Now this time when I drew it out, since everything except for this resistor is 1 ohm, I didn't bother to even put that number in there. Putting a number 1 in there is not really necessary when you write any type of equation with any variable. The fact that the variable's there, the unknown's there, the letter's there, just means it's got to at least be 1. So when we look at this one, we'll look at it and work it out. Now I'm going to do another video on dealing with current directions and stuff. You know, which way does current flow and why there is 2 different types. I'm going to go a little more deep depth into that. But due to my training and many years of habit, through that I'm generally going from positive to negative. I'm not saying that's the correct way. In fact, as far as I'm concerned, it makes no difference. And when I actually go on the other video, I'll show you why it really makes no difference. Don't let that hang you up. If you want to go the other way, it's just perfectly fine. The biggest thing is what is known as sign convention. Because we're using algebra to do this, our signs are extremely important. Now, we all know, or should know by now, that on a battery you have positive and negative. The long blade, long line is positive, the short line represents negative. I'm using conventional current, so I'm going to go from positive to negative. It works the same as going the other way, in which I will show in the other video. But if I'm going, the wires themselves, our connections, we consider ideal. They have no resistance whatsoever, so there's no voltage drop in there, so I don't have to worry about signs on the wires. So I'm going positive, negative, so I go positive until I run into something that will give me a voltage drop. So I go positive, following this loop, then I come down here, the first thing I'm going to hit, positive to negative, because I got a resistor here. It's going to give me a voltage drop. On the other side of that, though, will be positive. It has to be the other sign. Now I go from positive, negative, positive, negative. This is very important, and we'll go over it again, like I say, when I do the video, the next video, dealing with current direction and how why there is conventional current. Okay, why the predominant thing is from positive to negative. Alright, if you went from negative to positive, it still works out. Negative, positive, cross, negative, positive, negative, positive. So it's the same thing. It doesn't matter which direction you're actually going, as long as you keep those signs correct, because they're going to make a difference in our equations down here. So let's just look at this. I have positive 13 volts. I don't have to put the positive sign in there if it's the first number. Standard math rule. I can omit it. So I got positive 13, but I come here, I have 1 ohm times my unknown current. Well, I don't have to put the 1 in there. I already know it exists. So I left the 1 out. I just put I1 in purple. Hopefully you can see that on the camera. But it's negative. Because I come here, I see a negative. So it's negative I1. Then it's negative, because I come down here to this resistor. Now this, excuse me, the current through this resistor represents this current subtracting this current from it, because there's going to be, we're assuming that there's going to be a current going across here. So I've got to show that in my math. I'm coming down here that I'm going to lose some of this. So the current is I1 minus whatever's going across here, which will be I3. So I got to put that in there. Times 1 ohm. I didn't put the 1 in because it doesn't need to be there. I already assume and know it's there from math. But it's a negative quantity, because this is a quantity, I1 minus I3. According to Kirchhoff, everything has to add up to 0. So we equal 0. That's loop 1. Now we're going to go through all 3 loops, and then I'll go through all the rest of this. Loop 2, we start here. Again, positive 13 volts. Follow through, but now we're going to go through this resistor. Again, a negative there, positive here. Come around, negative and positive. So positive to negative, positive, negative, positive, negative. If you want the other direction, it still work. It'd be the same signs on exactly the way they are, but you'd look at them differently. So anyway, we start out positive 13 volts. We hit 1 ohm times I2. Again, I don't have to put the 1 in there. So it's just a negative I2. Negative I2. The next one, here, I2, if this current's going this way, then this current represented in here is going to be I2 plus I3. So that's the current that's going through here. We have to get that I3 in there because it's going to come to here and it's got to go somewhere. So it's I2 plus I3 times 2 ohms. And it's going to be negative. So we come negative 2, since we have a 2 here instead of a 1, we write it in, times this current as a quantity, I2 plus I3, and then that's going to equal 0. Now our last little loop, we decided to go this direction. And if you remember on the last video, that was actually the wrong direction. I thought I'd just go back over this exactly the way I originally drew it out, and then we'll talk about that again. So we decided to go this direction. You can go either direction, don't matter. So we start out with negative 1 times I1. We don't have to put the 1 in there, so I've got negative I1, our unknown current there. Then it comes down through here, I3. Again, it'll be negative and positive. So it'll be a negative I3. But this time it comes up and it sees a positive there, because this current's going that way. So it'll be a plus I2, and again that equals 0. Now don't let that confuse you. It's just the fact that this current, if it's actually going that direction, instead of flowing back this way, will flow this way. And this one's flowing this way. So they end up taking the same path and combining, and that's why we had I2 plus I3. That's how come here I don't have positive to negative, because I'm not going that way. I'll be going this way. I just wanted to get these 3 resistors for this loop in there. Now, what did I do the rest of the way? Well, basically all I'm doing is now I'm going to get rid of the parentheses. Okay, and that's all I did. I got rid of these 2 parentheses, so it's 13 minus I1 minus I1 again, because it's right here. But a negative times a negative, whatever's out here is outside the parentheses, is multiplied throughout inside the parentheses. So negative times a negative is a positive. So now I got plus I3 equals 0. Down here we had 13 minus I2 minus 2 times everything in here. So it's minus 2I2, again here, I2, and it's minus a positive I3. A negative and a positive multiplied together is a negative. So it'll be minus 2I3 equals 0. And all I did here is I just rearranged this. So it's I2 equals I1 plus I3. That's all I did with it. I just moved some stuff around, left I2 here, moved these 2 guys over on this side of the equal sign, and just gave me I2 equals I1 plus I3. That's all I did. Now we do what is known as collecting terms. Everything that is the same we add together. I1 and I1 here, these guys are the same, so I go 13 volts minus 2 I1s. One there, there's 2 of them. So it's minus 2 I1 plus I3 equals 0. Here it's 13 volts minus, but we've got 3 I2s. I got an I2 here and 2 more. Add those together, I get a minus 3 I2 minus 2 I3, and that equals 0. Now at that point I decided to go ahead and do a little more work with it. So what I did was I looked at this I2. In order to solve these two equations, because I only got two unknowns, I can solve them. Well, I actually got three, but I want to make it two. I need to do something with one of the unknowns. Well, I got two I3s, I got one I1, and I got one I2. So I go back to this and I look at which one would be the easiest to deal with. Well, I2, because it equals I1 plus I3. So I substituted this in place of this, and that's what's going on here. So we're taking this equation and turning it into this. 13 volts minus 3, which was times I2, but I2 is I1 plus I3. So it's 3 times the quantity I1 plus I3, which is exactly the same thing as I2, minus 2I3 equals 0. And then all I did is got rid of the parentheses and collected my terms, which ended up being 13 volts minus 3I1 minus 5I3. That's it, because 3 times this negative times the positive makes it a negative. We have negative 3I3 added to negative 2I3 gives me a negative 5I3. Negative 3 times I1 gives me a negative 3I1. So that's what I ended up with right here. I brought that over to here. Now I have two equations, two unknowns. What I need to do is figure out a way to now further eliminate an unknown, one of the currents. So I look at it. The first one, I got 13 minus 2I1 plus I3 equals 0. Here I got 13 minus 3I1 minus 5I3 equals 0. Well, this and this are opposite signs. Addition would get rid of them if they were the same size. Well, that's easy. Just multiply everything on the first equation by 5. Since this is 5I3, make this a 5I3. When you do that, you make sure you multiply everybody else by 5. That keeps everything the same. By doing so, and I brought that down here, it just goes down here after it being multiplied times 5, it comes up to 65 minus 10I1 plus 5I3. Add them together. The two I3s are going to cancel out because 5 minus 5 is 0. So I lose those. I end up 13 plus 65 is 78. Minus 3 plus minus 10 is minus 13I1. Move this over here. I end up with 78 equals 13I1. Then all you got to do is divide out. Voltage divided by resistance gives us current. So 78 divided by 13 gives me my current, which is 6 amps. At that point, all I had to do was take that 6 amps and put it into one of the equations. The easiest one to find, or easiest one that would be easiest for it, which turns out to this first one right here before I multiply it times 5. If I take 6 amps, put it back in here, multiply it out, and do a little rearranging, then I can find out what I3 is. And that's what I did here. I have 13 equals 12, because 6 times 2 is 12. I moved it over on this side, so it's a positive 12 now. Minus, so this got moved over here, I3. Subtract 12 from both sides, gives me just 1. Divide it out, you end up with I3 equaling negative 1 amp. Now that's negative 1 amp. All it said means is that my loop was the wrong direction. It should be this way, and this current should be going this way. That's all that means. Instead of going that way, the current actually is going this way. That's fine. So that's 1 amp. Now all I got to do is figure out what's left. I have I1, I have I3, and I need to find I2. Well, I got a nice convenient place to substitute in. I2 equals I1 plus I3. I3 is 1 amp, I1 is 6 amp, 6 plus 1 is 7. Gives me I2 of 7 amps. Now we come back to here, because the current going back in the battery is this current and this current added back together. Remember, they came down here and they split. When they get back to this branching here, they have to add back together. So they go into the battery together. So I add those together. 6 plus 7. 7 amps for here. 6 for I1. 6 plus 7 equals 11 amps. And then I just took it one step further to find out what the equivalent resistance is here. What is the load on this battery? What does it actually see here? So you take 13, Ohm's law, 13 volts divided by the total of 11 amps, gives you 1.2 ohms. So about all I can say on it. This is one of the harder circuits that you'd ever work out, but most circuits will be reasonably simple to a certain extent. I mean, if you're ever going to work them out, but Wheatstone bridges are fun circuits to play with, and fun to work out. Just, the biggest thing is watch your signs. Matters not what direction you're doing the current, because the signs still work out that way. And if you end up with a negative current, no big deal. The number is correct. Like in this case, 1 amp is correct. It does have 1 amp going through it. The negative just says I actually had drawn the loop in the wrong direction. The current's going opposite of that. So that's all that means. So don't let that bother you if you do one of these. You work out a circuit and you come up with a negative current. That's fine. It just means that your current's actually going, the real life, the current's going the opposite direction of that. But the number will be the same. Otherwise, keep your, like I said, keep your signs correct. You pick out the number of loops or whatever you can. Use both rules if you have to get you the number of equations you need for the number of unknowns you have, and work them out. And then all you got to do is just the algebra. Just start breaking the equation down. If you have things like this where you have I2 plus I3, I1 minus I3, and you got these parentheses, and you got to start working it out. Just start working it out. Get rid of the parentheses. Combine your terms, get the equations down to the simplest form, start eliminating your unknowns until you get down to finally to one unknown that you can solve. So I hope that helped and is a little better, easier to understand. If not, we'll do another video on it. We'll keep doing this until we get this reasonably down pat, so that everybody kind of understands it. So anyway, on the next video we will discuss this current direction thing. And again, I'm not going to get in the debate because I really don't care which direction it is. I just follow a certain direction out of pure habit than anything else. If you were taught and everything and go the opposite direction of that, that's fine. Again, just as long as you keep your signs correct. And we'll go over that again because that's very important to keeping these equations correct. So on the next video, that's what we'll discuss. So thanks for watching, and I'll see you in the next one.